Welcome back, chemistry fans. What we are going to work on right now is the final topic in Unit 6. So this is topic 3. We're going to be talking about expanded octets. Let's jump right into it. Okay, so on the expanded octets, what you need to understand is that we have been working in a more idealistic world up to this point. We've said everybody wants 8 valence electrons around it. Well, you can see from this example of this molecule here, there's something else going on. If we look at that sulfur in the middle, it's got 12 valence electrons. That violates everything we've talked about so far with the octet rule. So why does this happen? How can it happen? So let's take a look at what occurs when it happens. So we have in this very small image here, which let me see if I can zoom in just a little bit here. Get this to go down. There we go. What we see here is now the opportunity for some increased numbers of atoms around the central atom. So we started off and we learned that there are these ones that are linear, bent. We talked about trigonal planar, trigonal pyramidal. We talked about tetrahedral. Well, now what I'm going to introduce to you is this opportunity for just a few more atoms around it. And when this occurs, we have these bottom 2 options here. Now, these occur only in the elements that have D sublevels. So you will not see an expanded octet with any of the elements that are in the upper energy level. So if we were to look at our periodic table here, let me discard this. That's an old warm-up for us. If we were to look at any of the elements in groups 1, 2, 3, 4, 5, let me erase all of this nonsense. Well, that got rid of the whole entire periodic table. So let me reverse that. Okay, so I'm just going to write on top of it here. If we were to talk about any of these elements above element 18, actually above element number 20, they do not have the opportunity. They are not large enough elements to expand their octet. So it's only whenever we have elements below this, and specifically, it's usually even just the first row, because there are a few exceptions with sulfur and chlorines that can do this. But generally speaking, it's the ones that have these increased D sublevel potentials because the atom is getting so much larger. Okay, so with that said, let's go back here and see what happens is that the atoms start now coming around it in more equatorial planes, like the z-axis going straight up. You'll notice that there are some atoms that come straight out of the center, as well as these 3 that go around the middle. Well, then if we increased it by 1 more atom, we'd have 4 around the horizontal plane, and we have these 2 coming out of the north and south poles. And the names of these 2 that we're going to be working with is the trigonal bipyramidal and the octahedral. So we just have to be able to draw these. And the good news is what happens, we lose the need for the formula. Now I'm going to back this back out and we're going to deal with a couple of new definitions that we also need to add into our comprehension of these expanded octets, which will aid in us. So we're going to run into a word called a ligand. A ligand is just simply any element, ion, compound, polyatomic ion, anything that bonds to the central atom. We will refer to this as a ligand. A ligand is just something that bonds to the central atom. So it's very flexible in what it can be. Now, one of the things it does is it donates its electrons. So it has some extra electrons that it will donate to create the bond. So it is not one where it's necessarily sharing the electrons. It's that central atom is taking the 2 electrons and now they're sharing. So the central atom, it's not able to offer any more electrons. It's just that it's able to accept more electrons. All right. So next comes a free radical. Well, sometimes there is a central atom that does have a lone electron, an unpaired electron. It's not one that is out there satisfied because it has a filled sublevel or a filled orbital. And so it's looking for someone to pair with. And so a free radical is any of those materials, these species as they are sometimes called, which have one electron, an odd number of electrons, if you will, in its valence shell. And it's looking to try and get itself satisfied to create the stable octet or to create the stable expanded octet. And so this empty space that you saw in the previous image, that's where bonding is going to occur. And so that's why they call them free radicals, is that they are looking for someone to bond with. So they are ligands that are trying to find someone. All right, well, I guess they could be a central atom as well. Never mind. So it's just someone who's looking to create a bond. All right, so one of the other details that we have kind of skated over is the fact that there are stable duets, and that only happens with hydrogen. We have talked about that, but there are some other exceptions. It happens with beryllium, boron, and aluminum. Those three elements, if you notice, they are at the very start of the periodic table. Let's see if we can get them circled up here. Beryllium, boron, and aluminum. Those three, for whatever reason, they happen to form stable hexets. They like forming something that is not a stable octet, and they are satisfied fully. So if you ever given this molecule, such as boron trifluoride, don't panic and try and say it can't exist. There are three of these elements on the periodic table which create these incomplete octets, or you could call them sextets. And so they can bond and they are happy as long as everyone has the correct number of valence electrons used around them, then we are good. Now, we come to the final part here, the expanded octets. And with the expanded octets, the method we are going to use is we're going to start just counting the number of valence electrons. And if we have any extra at the end, they will be a pair of unshared electrons around the center atom. The elements going around it will never violate the octet rule. It's only that center atom that's going to be violating its octet rule. Okay, now one other detail that's in here is sometimes, and it's so rare, I don't anticipate I would ever ask this, and I don't see that it would ever be a part of an AP exam where we would have an uneven number and something called resonance starts to occur, where this one free electron starts to act alone as its own bond. So it's an odd number of electrons around the center atom. So they have that odd electron molecule. I don't think that that's ever going to occur, just making you aware of this NO2 molecule. It's a very rare one. All right, so we've already looked at these trigonobipyramidal structures. And again, what you notice is it has bonds coming out of the north and south poles, and then it has a trio, a triangle, if you will, around the horizontal plane. Now, we will talk about bond angles in the next unit, so I wouldn't worry about seeing that right now. The other molecule that we will create is an octahedral, and it has a north and south pole as well, but instead of having a triangle sitting around Earth's equatorial plane, it has an X, or it has a square, a box, if you will, that goes around that middle of that S in this molecule. Okay, now here is where it gets a little bit weird though. What if we don't have 6 or 5 atoms, but we still have extra electrons? Well, then we start getting into other shapes that we need to be aware of what their names are. We have the seesaw, the T-shape, and it could be a linear. In these examples, only where we have X's is where there is an atom. The A is the central atom, and the X's are the ones that are around it. So these E's over here, those are extra electrons. And so you notice we're starting to get fewer and fewer as we go along. And eventually it ends up that you would have, yes, a stable, an expanded octet, but not based on what you think because it has extra atoms, but because it has extra electrons. So these other shapes we're going to have to become familiar with. And the way that I try and get you to memorize this, if you see that it has 5 ligands, there's that term again, 5 places where things can bond around it, whether that be extra electrons, whether that be extra atoms, then it's going to be this trigonal bipyramidal. Where we lose atoms is on the horizontal plane. They start to drop off atoms on the horizontal plane only for the trigonal bipyramidal. Because if we then look at the octahedral, the electrons start adding on the north-south pole region. So it's going to be weird, and we're only going to be able to see this once we start to practice. Okay, so here are a couple of examples of these expanded octets, each one of them having more than the necessary normal 8, because if we look at each one of these bonds, that's 2, 4, 6, 8, 10, 12 electrons, 2, 4, 6, 8, 10 electrons, and 2, 4, 6, 8, 10, 12 electrons. So it depends on how many electrons we have as to how we will give their shapes. So we've got 4 examples. Let's jump right into them. We're not going to do want minus have anymore. What we're just going to do is count how many valence electrons they have. So borons and the 3 fluorines. Each of the 3 fluorines have 7. And the boron, we will take a look at where it is. We haven't ever probably even bonded with anything boron. It is in the 3rd. It has 3 valence electrons. So if we are counting up what we have here, we have a total of 24. I'm going to put the boron in front. I'm going to put fluorines all around the boron. I know that there have to be single bonds. We'll usually never have double bonds. That's a very rare in an expanded octet scenario. So I've only used up 6 right there. So I'm down to 18. Now I'm going to make sure that the Fs all have have stable octets. They must have their stable octets. So that's 6, 12, and 18. So that means I have filled up. I don't have any extra. So that boron does not get a stable octet. It's satisfied with a stable sextet. All right, next, ICl4, that should be a lowercase 4. I'm not sure why it didn't transfer over that way. So I've got I in the middle because it's the first element listed. I've got Cl's on each of the corners. I know that there will be single bonds on each of those Cl's. I know that I must fill up each one of my Cl's at least. Now, let's do the have. How many valence electrons does it have? Each one of those elements is a halogen. So that is 7 for each one of those. That is a total of 35. 5 times 1, 2, 3, 4, 5. 5 times 4. 5 times 4. Yeah, that's 5 times 7 is 35. All right, so we've got something weird going on here. I'm not sure exactly what we've got. We're going to figure this out. So I've got 35. Let's go ahead and then subtract from it the 8 that we would have for the valence electrons on that one. I'm sorry, for the bonds on that one, and that would be 27. And then I would subtract 6 extra electrons, unshared, unbonded electrons around each of the chlorines. 4 times 6 is 24. That would mean there's 3 extras. Boom, boom, and boom. So here's one of those rare circumstances where we would have an odd number of electrons in here. What is the name of the shape of this one, by the way? This is called a T shape. And over here, this one does have 6 ligands in it. So it should be an octahedral. However, there are 2 locations that are not atoms, so they don't bond that way. So in an octahedral, what drops off are the north and south poles. And so we end up only with a square. It's a weird shape. It's just called a square planar. Square planar. All right, let's do the last one, SF4. So I've got, and I'm going to move to a new page here so that we can actually see it, SF4. Well, we've run out of room. So let's come over here. Let's put the SF4. And let's do our valence electrons. So 6 for the sulfur and 4 times 7, that is 28 for the fluorine. So we get a total there of 34. Now we can subtract the 8 bonds for 2 times each one of the bonds, 8, and that gives me a total of 26 remaining. So now that I have 26, now I'm going to put in the extra electrons for each of the fluorines. And whoops, I put one too many there. And so what we end up with is 6 times 4 is 24 minus 24. And what we have are 2 extra electrons. So where are we going to put those 2 extra electrons? They go around the center atom, around that S. And so I get 2 extra electrons. So that means I have 5 ligands. That means this is a trigonal bipyramidal. So it's the triangle shape with atoms coming out of the top and bottom. Now, in the triangle shaped ones, what happens is we lose that horizontal equatorial plane electron. And so what we end up with is something that ironically is described as it looks. It's a teeter-totter. It's called a seesaw. It's called a seesaw shape. All right, this is everything that I wish to share with you. So thank you so much for staying with me on the octet rule, the expanded octet rule. Thank you, and we will practice it in class again. Bye-bye.